All right, let's go ahead now and talk about a different way of doing these problems. This is called the tabular method, integration by parts using the tabular method. May or may not be in your textbook. I have a PDF on integration by parts using the tabular method. Gilman wrote a paper on it, which you can find on the internet. Horowitz did as well. It's a chapter in his book. There are different places that you can find it out there on the internet, or you can just watch this video, and that will teach it to you as well. So it basically does the formula from the theoretical part of integration by parts, but it just takes care of the details. It sort of automates when you have to repeat integration by parts over and over. If you only have to do integration by parts once, you might as well, you really are just doing the theoretical formula. The integral of u dv is equal to uv minus the integral of v du. It's not saving you any time to do tabular, because tabular is that formula. Tabular is effective when you have to do integration by parts over and over again. So steps to doing integration by parts with the tabular method. Now I go through the steps here and I do it in words, all right? Which is not always the greatest way to teach something. The best way of doing it is to just show you, and then it will make a lot more sense. I'll talk you through the words just so you have them in the video, but I expect that you're going to get to the end of the words and say, I have no idea what she just said, and I have no idea what to do. Don't sweat it. I'll show you. Identify that you need IBP. You have in the integram two things multiplied together that are fundamentally different types of functions. Identify who's you. Use Liete. Logarithms first, then inverse trig, then algebraic, then trig, then exponentials bringing up the rear. Everything else in the integram, including that differential, has to be dv. All right? Create two columns. Well, I actually did this before. I just didn't point it out. I had u on the left and I had dv on the right. So it's really essentially the same. I'm going to label the u column d for derivatives, and I'm going to label the dv column I for integration. All right? So I'm going to take the derivative of the left and I'm going to integrate on the right. Well, that is what I did with the formula. So far, it's no different. Then I'm going to place the value of u at the top of the left column, the derivative column, and I'm going to put the value of dv at the top of the right column. You can skip writing the differential. This is kind of weird. You don't normally do this. In fact, I told you, you do it in my class, I'm going to cut you off at the knees. If you want to write the differential, write the differential. All right? I do most of the time because it just bugs me not to. But that's what we're doing, is we're going to be integrating the right side over and over again repeatedly. Using lots of space in between, keep your rows level. Each time you compute a derivative, that goes down one row. Each time you integrate, the result is the next row. Not every row of the integration process. Do that on your scratch work. The next row is the result of the integration. So you have u, next line, derivative of u. You have dv, next line, the integral of dv, which is v. You just integrated it. So you got v. Then, if the derivative of u is such that repeated differentiation will lead to the number 0, we're going to do something special. What did I just say? Okay, for example, x squared. Let's think about x squared. We have that in the integral that we just evaluated. If I take the derivative of x squared, and this is my derivative column, the derivative of x squared is 2x. The derivative of 2x is 2. But the derivative of 2 is 0. This is what I mean by the derivative column zeroes out. If I continue to take the derivative of a polynomial function, I'm eventually going to get to 0. So basically what we're looking for here is a polynomial function. So if I have a polynomial function, I'm eventually going to get a derivative of 0. Woohoo! We love these guys. These are like the best, all right? If we have that, where the repeated process of differentiation leads us to a 0, and each one of these counts as a row, then we're going to do that. We're going to create a row for each new derivative until we get to 0. This is going to be my last row. Now I've got to take another column over here, which is my integration column, and I'm going to have my dv. And I'm going to have to integrate that dv one time to get to here, another time to get to here, and one more time to get to here. I need exactly the same number of rows. So the number of times I do the derivative is the number of times I integrate the dv side, right? So we're going to integrate until we reach the same number of rows as we have in column 1. Then what do I do? All right, well, let me scroll back up so that I can show you a little bit. So I've got a dv equals something, all right? And then I integrate it and I get something else. Call it a star. And then I integrate the star and I get, I don't know, I'm running out of symbols, a square. And then I integrate the square and I end up with a happy face. All right, so now can you see what I've done? I've created 2 columns, the u column, which zeroed out through repeated derivatives, and a dv column, and I integrate to get from this line to this line. This is the result of the integration. Then I integrate again, and then I integrate again. This one is probably not 0. In fact, it won't be 0, right? Can't be 0, right? Now what I'm going to do, go back to the words. We'll come back to this as well. Starting with the value of u, which is in column 1, row 1, and the integral value of dv, which is v, column 2, row 2, connect it with diagonal lines from the upper left to the lower right, precisely 1 row down. This was the original formula, uv minus the integral of v du. Let's look at it. So coming up here, this was actually my v. So this is uv, and then this row is my v du row, yeah? But I had to do integration by parts more than once. So I want to connect this one with this one, the 2x with the square, and the 2 with the happy face. I'm going to go exactly 1 row down each time. Right? Upper left to lower right, 1 row down. Upper left to lower right, 1 row down. Upper left to lower right, 1 row down. Notice I can't do it on the last one in the left column because I don't have a lower right to go to. But what was the pattern when we were doing this in the theoretical formula? We went down u times v, and then we came straight across the bottom row. We had the integral of v times du. So we're going to go straight across the bottom row like this. This is going to be the part that hasn't been integrated yet. So now what do we do? I've done integration by parts multiple times. That's where this comes into play. But the integration by parts has minus the integral of v du. So if I keep subtracting stuff, if I subtract to subtract, that's actually addition. If I subtract to subtract, that's actually subtraction. So I get alternating signs. So these are going to alternate in sign, where the first one is positive u times v. So the next thing we're going to do, and I'll add this in blue so it pops out, is a plus, then a minus, then a plus, then a minus for the last one. Whatever number of rows you have, you're going to have that many different signs. So you've got a plus for the first diagonal, a minus for the second diagonal, a plus for the third diagonal, and a minus for the bottom row, right? Now, what do we get when we do this? The integration by parts is going to take the product of the diagonals with whatever sign you had alternating in blue. So this first one is going to be x squared times star, and it's going to be positive. So let me write it down here, x squared star, and it's positive. And the next one is going to be subtracted because I'm alternating signs, and I've got 2x times the square. So I've got minus 2x times the square. And then the next one alternates again, so it's back to positive, so I have 2 times the happy phase. And then the bottom row is that last part, the integral of v du. It hasn't been integrated yet. So I have minus the integral of the product of the bottom row, minus the integral of 0 times happy phase. And remember that happy phase technically has the differential attached, all of these in the right column. So I've got the differential. But if I have 0 in the integrand, then the whole integrand becomes 0. What's the integral of 0? 0. So this last integral actually drops out. In other words, when we have a polynomial function and the derivative of it zeroes out, this last row isn't actually going to end up needing to be integrated because it's just going to be the integral of 0, which is 0. So the integration by parts becomes x squared star minus 2x squared plus 2 happy phase. If I could draw better, I'd have better symbols. But that's basically it in a nutshell. So it takes care of the details for you. Now notice that up here in this last method we did, it got really messy, right? I mean, remember what we had to do. I did the integration by parts, u times, where is it, v, that's one row down, right? The actual result of the integration, minus the integral of v du, that's straight across that row. That is tabular method. But then I had to do it again. And when I used the theoretical formula, it got pretty gnarly, right? If that's still a word. It's pretty nasty, all right? We've got all this stuff needing to be substituted in here, and you've got negatives, and I even messed up a negative over here because there's so many negatives running around, and it's hard to keep track and very easy to mess up. This is where tabular can be very, very helpful, all right? So what we're going to do now is we're going to go ahead and we're going to skip the next part for a second. And we're going to redo example 3, the one that we just did about 10 minutes ago. We're going to redo it now, but we're going to use the tabular method. And then I'll talk about the next parts of using tabular method for integration by parts, right? So let's take a look now at this one. So I've got x squared, again, is algebraic. So it gets to be u. And e to the 3x dx then gets to be my dv. All right, so this is what I have. Now let's remember how to set up tabular. Okay, so what we want to do is we want to set up a u column and call it derivatives. So we have u equals x squared, and this is my derivative column. And I have dv is equal to e to the 3x, and yes, I like to put my differential, which is dx. Okay, now I'm going to take the derivatives on this side, and I'm going to integrate on this side. Now, you may need another sheet of paper because we're going to have to integrate this in one line, right? So maybe I should move this over a little bit so that I have space over here that I can actually do my scratch work. So I have dv equals e to the 3x dx, and this is my integration side. Remember that we've already integrated this one like 3 times already. So remember, you would do u substitution, u is 3x, and so the derivative of u is 3 dx, and so dx is du over 3, and so you end up with a 1/3. So when we end up integrating that, and I'm not going to go through those steps because I expect that you do know how to do that, we end up with 1/3 e to the 3x, right? That's my next row. Now, if you do need to go through the steps, come over here further to the right and do it to the right. Don't do it in between the rows because you got to keep those rows even. And we want it to be nice and neat so we can follow it. Now we're going to take the derivative on the u side one time to match the rows, even them up. So the derivative is going to be 2x. And then I need to take the derivative again, so it's going to be a 2. And that means I need to integrate this again. All right, so if I integrate this again, it's 1/3 times the integral of e to the 3x, which is just going to tack another 1/3 on the front. So this time I'm going to get 1/3 times 1/3 e to the 3x. And again, we've kept our rows even with each other. And then I want to take the derivative again one more time, which will zero it out, and it will go to 0. And when I integrate this side, again, it's 1/9 times e to the 3x, which gets another 1/3 at the front, which becomes 1/3 times 1/3 times 1/3 e to the 3x, or 1/27 e to the 3x. Now I'm going to connect using diagonal lines, upper left, lower right, one row down. So I'm going to go ahead and make these blue. One there, one there, one there. Those are my diagonal lines. And then the last row is that integral of v du. So I have one coming straight across the bottom to finish it off. These have to alternate in sign, starting with a positive, because the theoretical formula is positive uv minus the integral of v du. So we have a positive, then a negative, then a positive, then a negative. So this means that what we have over here as the integral from 0 to 2 of x squared e to the 3x dx is equal to, multiply the two together, so x squared times 1/3 e to the 3x becomes, well, 1/3 x squared e to the 3x. Evaluate from 0 to 2. Remember, the limits of integration have to be evaluated on every term if it's a definite integral. Then we want to subtract the product of 2x times 1/9 the 3x. So that's going to be minus 2/9 e to the 3x, evaluated between 0 and 2. And then we want the next diagonal, which is going to be a positive 2 times 1/27 e to the 3x, which is going to give us plus 2/27 e to the 3x, evaluated between 0 and 2, which brings us to the last row. The last row is not a diagonal. It's still going to be a product, but it hasn't been integrated yet because it's not a diagonal. On the diagonals, the integration's already taken place. It's the uv part. The last one is the integral of v du. So we get the product of those two inside of an integral, and it happens to be negative, and we have 0 times 1/27 e to the 3x with the differential dx. Remember that all the ones in the right column actually have a differential attached. We just don't always write it down, right? And then what do we want to do? Well, we want to evaluate what these are and see what we come up with. So let's see what you come up with when you do this. Go ahead and pause the video, work it out, and then turn it back on to compare your answer to mine. Okay, I caught one error. I forgot and didn't have my x down here. This should have been 2x times 1/9 e to the 3x, and I forgot to write my x. Caught it when I was doing the integration by parts. So when you plug in all these numbers, lo and behold, you get the same thing we got the first time. But when you compare the work done, even though this last part of plugging in the limits of integration is kind of messy, the tabular part, which represents the multiple levels of integration by parts that we had to do, is actually quite simple. And it's easier to write down the result, this line right here. And so it becomes a much simpler thing to manage the details. It's not any different. It really is the theoretical process. It's just a technique for keeping track of the details of the theoretical process. So now let's go through and let's do another one that's slightly different than what we've done before. This is one that's going to repeat. Now, how is this different from the one we just looked at? We have e to the x and sine of 2x. So let's pull these apart. We have e to the x as one of the functions inside of the integrand, and this is exponential, so it's e level, which means it's not u. And then we have sine of 2x being the argument to the trig function. It is a trig function, so it's t level. Remember, our mnemonic device is liete, and we have a t level and an e level. So that means that u is going to be the sine of 2x, and our dv is going to be everything else, which is going to be the e to the x dx. Now, we have a problem with this one compared to the last one, in that the derivative of sine of 2x is never going to disappear, right? It's not going to. It's going to become, well, 2 times the cosine of 2x, and then -4 times sine of 2x, and then after that I'm getting lost with the chain rule. But basically, it's never going to go away and it's never going to zero out. So what do we do in that case? So let's come back up here to our steps and note that then here in step 6 it said if the derivative of u is such that repeated differentiation will lead to the number 0, do all this stuff that we did and then we practiced. Okay, well, it doesn't lead to 0. So now what? Part B. If the derivative of u is such that repeated differentiation does not eventually lead to 0, but you do have sine or cosine, haha, in there, then the pattern will eventually repeat. Because whether you're taking the derivative of sine or cosine, or you're integrating sine or cosine, it's a pattern that repeats to a multiple every 4. And so we know that we get a multiple every 2. We get back to the original in the 4 if the argument to the trig function is just x. If it's not just x, then we get to a multiple. So now what we want to do is we want to do integration by parts, and we want to take precisely 2 steps of the differentiation integration process as in the previous pattern. So we want to do this twice. Why twice? We want to end up coming back to a multiple of what one of the first values was, the one with the trig. So if we start with sine, we want to either take the derivative twice till we get back to a multiple of the original sine, or integrate twice till we get back to a multiple of the original sine. And then we stop. If you don't stop, this pattern just goes forever and ever. You're never going to be done. So we stop when we get to a multiple of the original. Then we repeat the same process. We take the value of u, column 1, row 1, upper left, and the integral value of dv, that's v, column 2, row 2, 1 row down on the right, upper left, lower right. We multiply them with diagonal lines. We repeat the diagonal lines for the second row and the third row, right? So we've only done 2 iterations, right? So we've only done it twice. Then we're going to have the last row coming across. So let's say that we have our u here, which is square, and dv here, which is, I don't know, star. And then we do the derivative of u, and we end up with, oh boy, I've got to come up with better shapes, rectangle. And then that's once. I said do it precisely twice. So we do it again, and we get some kind of constant, maybe 3, maybe 5, maybe 42, could be e, could be pi, could be any constant under the sun, positive or negative. But we get back to a multiple of the first one, if this is the trig function. If the trig function is here, it would be the same thing, but it would be showing up over here. So what we're going to do is we're going to do precisely 2 iterations, whichever side the trig is on, it doesn't matter. We'll eventually get back to a multiple of the original. And then we're going to connect just the way we did before. So I'm going to have a happy face, and then I'm going to have a frowny face. Sorry. And then we have the same thing. We connect them like this. But you may say, but it didn't zero out. That bottom one's not going to zero. No, it's not. But what does it have in it? It has a multiple of the original integral. Ha-ha! In fact, it's going to be a multiple of the integral we're trying to evaluate. So let's see how this works out. What's going to happen is we're going to get a multiple of them, and they're going to be the same, but with different constant coefficients. So we're going to move the like integrals together and then solve for it. And let me show you what this looks like. So this would be example number 4. Okay, so I've established that e to the x is exponential. It's not u. And sine of 2x is trig. T comes before e, so sine of 2x is u. So I've got my derivative column here, and I've got my integration column here, and I'm going to do these with integration by parts. Can I do it with the formula? Absolutely, you can do it with the formula. It's just a little more writing. You've got a lot of nested parentheses. You got to really be careful with those negatives. That's the only difference, right? I prefer tabular because, as you've seen a couple times already, the details sometimes, yeah, those negatives have a way of creeping away from me. So I'm going to apply the process exactly twice. So I'm going to take the derivative of sine of 2x. Don't forget chain rule. Derivative of 2x is 2. So the next line down is going to be 2 cosine of 2x. That's one line down. Now, I've got to balance that out by doing the integration of e to the x dx. Well, I love e to the x. This is why we love e to the x. It's so awesome because it just gives us e to the x. And then I'm going to do it again. So I've got another dx over there. So I have to do this exactly twice. Why? Because I could keep back to a multiple of sine of 2x. So I take the derivative of 2 cosine of 2x, which gives me a negative 4 sine of 2x. Now, this is a multiple of the original. And that's what I mean. It's negative 4 times that. This is why we go twice and stop. Once you get a multiple of this, stop. All right. Now I've got to integrate the right-hand side to balance out. And the integral is again e to the x. And then I'm going to do my process. So I'm going to have upper left, lower right, upper left, lower right, bottom row needs to be integrated. Okay, so now I'm going to connect. Plus, minus, plus. So what am I doing? The integral of e to the x, sine of 2x, that was my original integral. That guy is equal to, through integration by parts, tabular method, is equal to the product of u times 1 line down v. So I'm going to put the e to the x at the front. That way it doesn't creep inside the argument to the trig function. E to the x sine of 2x minus, and again, I'm going to pull this e to the x that I have here in front of the cosine. So I'm going to have minus 2 e to the x cosine of 2x. And then I've got on the bottom row, I've got a negative. This is positive and that's positive, so it's going to be negative. And I'm going to have a 4 e to the x sine of 2x minus the integral. Remember that bottom row hasn't been integrated. I can move the 4 on the outside. Oh, wait, I said I was going to move the e to the x to the front. E to the x sine of 2x dx. All right. And you're looking at this going, yeah, that didn't help me much because I don't know how to integrate that. That's kind of where we started. Yeah, It is. It's a multiple of where we started. Notice that this integral and this integral are identical, except this has a -4 on the front and that has a 1. That means they're like integrals. They're like terms. Let's just move them together. And you're like, can you do that? Yep, you can do that. So we're going to add 4, the integral of e to the x sine of 2x dx, to both sides of this equation. Well, then how many integrals of e to the x sine of 2x do you have on the left-hand side? I'd say you've got 5. 1 plus 4 gives you 5 of them. 5 integrals of e to the x sine of 2x dx. And it's equal to e to the x sine of 2x minus 2e to the x cosine of 2x. Now, what's the only thing you have left to do? You have 2 things left to do. What 2 things do you need to do? Well, I didn't want 5 times the integral. I wanted the integral. So I need to divide by 5. And it's an indefinite integral, which means when I'm done, it's only good up to a constant. So I need a constant. So I could put the plus c on now and then divide by 5, or I can divide by 5 and then add the plus c. But when I'm done, I should have, and I could take the e to the x out if I wanted to. Yeah, there's always stuff you can do to write it in a different form. But basically, the integral of e to the x sine of 2x dx is equal to 1/5 e to the x sine of 2x minus 2/5 e to the x cosine of 2x plus some constant. Because this is an antiderivative function. Indefinite integral, it's got to be an antiderivative function. We got to have that c. Where did the plus c come from? Well, it came from over here. All right? Whenever we have indefinite integrals, we have a plus c, and that's it. Isn't that beautiful? Isn't that amazing? I mean, it's just incredible, right? You look at it, it's beautiful, right? So this is what we do when we have something that doesn't zero out, but it repeats, like sine and cosine. Those are basically our 2 that repeat. Okay, let's take a look at another one and see what else we need to do. And if you were paying attention, you also noticed that the steps to tabular had 3 parts, A, B, and C. We've covered A. What if you have a polynomial and it zeroes out, the derivative? B, it doesn't zero out, but it's trig, it's sine or cosine, so it repeats. And C is none of the above, okay? So we haven't talked about C yet, and we'll get to C. All right, let's take a look now at example 5. Example 5 is one where we really have to do some fancy footwork, all right? So is this one that I would expect my students to be able to do on their own on the homework? Probably not. Probably not without a hint. If I gave them a hint, then I think they could get further most of the way through. Some of them will get stuck at some point because there is a trick later on. Trick means technique, right? So technique of how to integrate something. But with a hint, they could probably get pretty far, if not do the whole thing. But without the hint, it'd be very difficult. I might give it on the homework, but it would be a stretch problem, right? I'm not really expecting you to get it. So what's the key here? Remember what I said. U isn't a problem because we're taking the derivative of it. dv is a problem because it's got to be something we can integrate. Now, I could integrate x e to the x, but then that would leave u to be 1 over x plus 1 quantity squared. Remember, these have to be multiplied. So division is out, guys. This is product, right? So I don't really like that idea. Could I integrate the more, it's the fraction, right? That's really stressing me out. I know I can take the derivative of x e to the x. I could take the derivative of 1 over that, but it's going to get nastier. But which one could I more easily integrate? Well, 1 over x plus 1 squared is the value when you end up integrating. What do you get? I mean, how can you do that? When you look at that, if it's the derivative of something and you're integrating it, don't you get back to something that you can do? I mean, wouldn't that be relatively straightforward to integrate? In other words, this time, my u is a combination of functions. So it's not strictly a Liete problem, right? So it's that part C. It doesn't repeat and it doesn't zero out. It's something else. So I got to try a trick. And the trick is look for something that I can integrate pretty easily. Now I could integrate either one, but I'd have to do this one by parts. And the derivative of the fraction would just, it would get worse, right? I mean, I'd get more fractions. The fraction's not going to go away. So I think probably we're going to try something like this, where we have 1 over x plus 1 quantity squared dx. Now, could I integrate that? Yeah, I think I could. At first, I was thinking it was arctangent, but it's not arctangent, is it? Right? That would be x squared plus 1, not x plus 1 quantity squared. Well, if I integrate it, let me come over to this side in another color and just integrate this. If I integrate, can't I just write this as x plus 1 quantity to the negative 2 dx? Yeah, I can. And that makes it a little bit simpler because now I can do a u substitution. Well, I've already got a u, so let's use omega again. I can say that omega is equal to x plus 1. If omega is x plus 1, d omega dx is 1, so d omega equals dx. Oh, well, then this just becomes the integral of omega to the negative 2 d omega. I can integrate that, right? So this is u substitution. I can integrate it. What does it become? Yep, think about it for a second. You basically add 1 to the power, so it becomes negative 1 divided by the new power. So you end up with negative omega to the negative 1. And remember, we're choosing our constant there to be 0. And so we end up with negative 1 over x plus 1. All right, did that help? I don't know, maybe. Let's see what happens. Again, would I expect a student to be able to do this from the beginning without a hint? No. All right. How did I know to do this? A lot of trial and error and a little bit of looking at the solutions manual to get the hint of what to choose for u. So now I've got u as x e to the x. I've got to take the derivative. So coming down one line, my dv was 1 over x plus 1 squared dx. And so my v becomes this negative 1 over x plus 1. So now I've got to have one row down for this one over here. Again, this is going to be whether you're doing tabular or the theoretical formula, it's the same process. So I need the derivative of this. Well, this is a product, so I need the product rule. That's where we started today. So the derivative of x is 1, and so I get e to the x plus, and then x times the derivative of e to the x is e to the x. So I have e to the x plus x e to the x, all right? That's basically just using my derivative formula. And remember that I'm abusing the notation, so this is my du, and I'm going to swing the dx around to the other side. So I'm going to put that in parentheses and put the differential dx outside of it. Now, this is not one that zeroes out. And this is not one that has a trig function of sine or cosine that repeats. So I'm going to only be able to go one level before I need to reevaluate. So might as well use the formula instead of tabular, even though it's really the same thing. because I am connecting these two and these two, that with a plus and that with a minus, and that's my formula. So u times v minus the integral of v du. So let's go ahead and write that down. So I've got the integral of x e to the x over x plus 1 quantity squared dx is equal to x e to the x times a negative 1, so I'll put the negative on the front, over x plus 1 minus, oh, now wait a minute, I've got lots of minuses running around, minus the integral of the product of the bottom row, but I've got a negative in this factor right here. So I've got a negative times a negative, and this is all positive. So that basically means it's going to end up being positive. So this is going to be a plus, and I'm going to have e to the x plus x e to the x dx times that 1 over x plus 1, which I can write in the denominator, right? Now, when we're looking at this, this is a tricky one coming out of Cal 1. So when we're looking at this one, kind of stare at this for a second. This guy is done, right? He's done, he's evaluated, but this one's not done yet because we have to evaluate the integral. Well, I could take an e to the x out. Oh, bingo! If I take an e to the x out, I get an x plus 1. Got x plus 1 in the denominator. So then what I'm going to do, since I left some space here, is I'm just going to write directly above it, and I'm going to reorder. So I have e to the x times x plus 1. My x plus 1 is canceled. So that basically becomes the integral of e to the x dx, which is e to the x. And so now I can write that down. So I have negative x e to the x over x plus 1 plus e to the x, right? Now, don't forget that I also need a plus c because I just evaluated an integral, and it's only good up to a constant. This is the antiderivative function, good up to a constant. Now, you could leave the answer like this, or you could go a little bit further with algebra. You could get the common denominator of x plus 1 between these two, and you'll see that something kind of sweet happens if you do that. So if we do that step right here, multiply by x plus 1 over x plus 1, we end up with negative x e to the x over x plus 1 plus x e to the x plus e to the x over x plus 1 plus our constant. And then notice that when we combine with the common denominator, we have a minus x e to the x and a plus x e to the x, so they cancel out. We just get e to the x over x plus 1 plus a constant. Sweet. You gotta love it. All right. That makes sense to everybody? When you have an integrand that doesn't zero out, didn't start as a polynomial on the derivative side, and it's not a trig function so that it gets back to a multiple of itself, then you really should just go one layer down, one integration by parts process, and reevaluate, see what you can do after that. That's basically the strategy. Now what we want to do is take a look at another example. Okay, we have 4 more examples to get through, and we're going to go pretty fast through these. Basically, we'll look at the setup, and then we'll pause the video and write out the rest. We have x times the arctangent of x. I prefer the arc notation. No one's ever mistaken this one for a power. Students mistake this for a power all the time. That's not a power. That's the inverse tangent function. That's the one whose angle of the tangent gives you x. All right. Now, so you're finding the angle, not the value. So we've got an algebraic, which is x. We've got inverse trig. So we've got x, which is algebraic, and we've got arctangent of x, which is inverse trig. Now, if you remember the mnemonic device, it's liate. So we've got L-I-A-T-E. Whoever's on top or further to the left gets to be U. So we've got I level and A level. That means that X does not get to be U, which is kind of a bummer because x is polynomial. And if x were u, it would zero out, but it's not u. So it's not going to zero out, it's going to grow. So we're going to have u being the arctangent of x. Whoever is first in the mnemonic device gets to be u. It's unfortunate, we're not happy about it, but that's the breaks. So it's not going to zero out, and it's not sine or cosine, so it's not going to repeat. That means that our dv over here is going to have to be everything else, which is the x dx. And when we integrate x dx, we're going to get a 1/2 x squared. We're going to choose that constant to be 0 for that antiderivative. And then when we're looking at it, we know that it's growing. It's not going to zero out either, and it's not going to repeat. So we don't have case A or case B. So we're only going to do this process one time, and then we're going to reevaluate. So we're going to take the derivative of u, abuse the notation, and swing the differential dx around. And the derivative of arctangent is what I was thinking of on that last problem, but it actually wasn't arctangent. This one is, though, and it becomes 1/1 plus x squared. And then we're going to integrate x dx, which gives us a 1/2 x squared with a constant. But again, we're going to choose those constants to be 0, right? We're choosing the specific antiderivative. Now we're going to do the formula, u times v, upper left, lower right, product of the bottom row in the integral still. So now what we have is we have the integral of x, arctangent of x, dx, is equal to uv. So I'm going to put my 1/2 x squared at the front so it doesn't creep inside the argument to arctangent, minus the integral of v, which is 1/2 x squared, times du, which I forgot to include my differential. Remember, we abuse the notation and swing it around so that we have the differential to do the integration on the integral of v du. And then this gets multiplied by 1/1 plus x squared dx. Now the first part is done, so I don't have to worry about it anymore. It just kind of tags along and keeps rewriting and rewriting as we go through this process. And I can pull the 1/2 out, but then I have the integral of x squared over 1 plus x squared. And it kind of bothers me a little bit to have 1 plus x squared. So I'm going to put x squared plus 1 on the bottom. It's the same thing. I just commuted the two terms. And then I have the differential. Now, we have a problem, because if that's u, that's not du. And if that's u, that's not du. So we have to play an algebraic technique here, an algebraic trick for integrating this. It comes from Calculus 1, but I don't know if you saw it or not, so I'll teach it to you, which is basically what's called adding 0. So we're going to add 0 here. Now, what does it mean to add 0? It means you add a constant and you subtract the constant, or you add a term and you subtract the term, add an x term, subtract an x term. So I've added 1 and subtracted 1. Why would I do that? Well, let's split this now into 2 fractions. So I'm going to take this down into 2 fractions. So what I've got here coming down from up above is I've got this 1/2 x squared arctangent of x from uv minus 1/2 times, and now I'm going to do this next part in u in blue. So I've got x squared plus 1 over x squared plus 1 dx. That's the first part, minus the integral of 1 over x squared plus 1 dx. Now, obviously, the first one reduces to 1 dx, the integral of 1 dx, which will just give me an x plus a constant, right? I'm going to remember to put the plus c on at the end. I'm not going to keep track of all those constants in the interim, but basically this first integral gives me an x. Well, what about this one over here? Well, think about where we started with up here at the top. I took the derivative of arctangent and got 1/1 plus x squared. So if I wanted to have 1/1 plus x squared and I want to undo the derivative, won't I end up back at arctangent of x? Yes, I will. So this one right here becomes the arctangent of x. And this is inside our parentheses. And then I'm going to add a plus c onto the end. So I've got this minus a half multiplied by this right here. And so my final answer then becomes 1/2 x squared arctangent of x minus 1/2 x. Then I've got a double negative. So I get plus 1/2 arctangent of x. And then I've got my constant. And that's my solution. All right. So again, when you don't have something that's going to zero out on the derivative column and go to 0, or something that will repeat on either column, then you're going to only do the process one time and reevaluate and see if there's another way to integrate it. Let's look now at problem number 7. Problem number 7 is slightly different than what we have had before. On problem number 7, we've got arc sine of x dx. That's it. That's our integram, arc sine of x. It's just one function. But remember what I said, when you only have one function, you can always make two functions by letting one of the functions be the constant line y equal 1, or just 1 times that thing. So this becomes, in essence, the integral of 1 times arc sine of x dx. So our 1, which is really y equal 1, is an algebraic function. And our arc sine of x, of course, is inverse trig. So who gets to be u? Of course, inverse trig trumps algebra. So we have Liete, and we can then circle the I and the A. We've got inverse trig trumping algebraic. So we have u equal to, coming over here, arc sine of x. And our dv has to be everything else, which is going to be 1 dx. So then what we're going to do is we're going to take the derivative of arc sine. Do you remember the derivative of arc sine? I hope you remember the derivative of arc sine. But if you don't, remember that it comes from an application of the Pythagorean theorem. So we get 1 over the radical 1 minus x squared, swing the differential dx around to the right side. So this is one row down. This is our du. And when we integrate 1 dx, we get x plus a constant. We'll choose that constant to be 0. So this gives us v equals 2x. So now we're going to integrate. So we have the integral of arc sine of x dx, which is equal to u times v. So we have x arc sine of x, that's uv, minus the integral of v, which is x, times du, which is 1 over the radical 1 minus x squared dx. Again, this is one that didn't zero out on the derivative column. It didn't have a trig function that repeated. So we're only going to go one layer down, and then we're going to reevaluate this integral. Can I integrate this? Your gut reaction should always be u substitution if you can. If I let u be 1 minus x squared, is this a multiple of the derivative of it? And the multiple, or the derivative of 1 minus x squared, would be a negative 2x. So it is a multiple, right? So now I'm going to choose to do u substitution. So pause the video, go ahead and work that out, and then turn the video back on and see if your answer matches mine. So let's see what you got now that you're back. So we had to pause right here. We wanted to evaluate this. We decided it was u substitution, where u, or omega in this case, is 1 minus x squared. We did the u substitution. That gave us omega to the negative 1/2 power inside of the integral, which we add 1 to the power to get a half, divide by a half, which is multiplying by 2. So we get the 2 over 1 with the negative 1/2 on the outside. The 2's canceled, so we have a negative, the radical here. 1/2 power is the square root of 1 minus x squared. Don't forget you get the constant coming out of the integral. Now we want to substitute this in place of the integral, but the integral had a negative on the outside. So we have a negative times a negative, which will give us a positive, and then we have the radical, and a negative c is still a c. So we just call it plus c, and we're good. Okay, let's take a look at the next problem, which is somewhat similar. Looking at problem number 8, we have natural log of x dx. So we're essentially going to do the same thing. So go ahead and pause the video, work this one out on your own, following the steps we did last time, and turn the video back on and see if you get what I got. Okay, so we have the 1 again is algebraic, natural log is logarithmic, logarithmic trumps algebraic, so the logarithmic becomes u. It's not going to zero out, and it's also not going to repeat the pattern. So we are only going to go one layer down, so we're just applying the formula, u times v minus the integral of v du. So we calculate the derivative of natural log, it's 1 over x dx, and we compute the integration of dv of 1 dx, and it becomes x, where we choose the particular antiderivative so that the constants are 0. And then we have u times v, or rather u times v, minus the integral of v du. Now the x times 1 over x cancels, and we get 1 dx, which gives us x. So the result is what you probably memorized in Cal 1. The integral of natural log of x dx is x natural log of x minus x. It's a constant. And that's where it comes from. So you should have been wondering all throughout Cal 1 at the end of the course, why haven't they explained what that formula is or where it came from? We couldn't teach it to you till you had integration by parts. But now that you have it, you can stop memorizing this and just derive it. Things you memorize tend to kind of float away, but things you understand and can derive, you'll never forget. Now let's take a look at our last one, which is an application with a definite integral again. We have natural log with something on the inside, and we're integrating from 0 until 2. So when we're thinking about this one, we've got this same problem that we had in the last problem, which is we only have one function, which is natural log. So we know we're going to choose the other function to be a 1. So we're going to have a 1, which is algebraic. And then we're going to have natural log of x squared plus 1, which is logarithmic. And of course, the logarithmic will trump the algebraic. And so we know that u is going to have to be this natural log of x squared plus 1. And then our dv is going to have to be everything else, which is basically just the differential, the dx, with the 1 attached to it. And then we're going to take the derivative of the left and the integration of the right. So on the right, we're going to choose the specific antiderivatives to be the ones with constant 0. So we get v equal to x. And on the left, we need to take the derivative of this. So we get 1 over u, which is 1 over x squared plus 1, times the derivative of the inside, which becomes 2x. And so when we take the derivative of this, we should end up with du equal to 2x, chain rule, over 1 over u, wrong u. It's hard not to have the right one floating around. We've got so many u's going on, right? We've got the chain rule u, we've got the integration by parts u, and then we've got the u substitution u, which are not the same u's. All right, so we've got 1 over the argument times the derivative of the argument. That's a better way of saying it. Okay, so now we've got the parts we need in order to do one iteration of integration by parts. It is a definite integral. So remember, each part needs to be evaluated. So you may want to go ahead and pause the video here and see what you can work out. And then come back and see if your answers match mine. I'll give you a hint. You're going to need to add 0 in order to evaluate one of these integrals. So you're going to need to add 0 again. Remember that technique that we did earlier. Okay, let's see what you came up with. All right, so we have our du, we have our v. So we take u times v, which is x natural log of x squared plus 1, evaluated between 0 and 2. So that's going to give us 2 natural log of 5. The next part is going to 0 out. So we just get 2 natural log of 5 from the first term. Then we've got to evaluate this integral, this definite integral, still from 0 to 2. So we have x times 2x, which is going to give us an x squared. And I pulled the 2 outside. So I have minus 2 times the integral of x squared over x squared plus 1. This is where I said you need that technique of adding 0. If I add 1 and subtract 1, then I can get x squared plus 1 over itself, which is 1 dx, minus 1 over x squared plus 1. And the integral of that, of course, the antiderivative would be arctangent of x. Now, these both have to be evaluated between 0 and 2. So this is going to give you a 2. And this is going to give you the arctangent of 2 minus the arctangent of 0. That's the angle whose tangent is 2 and the angle whose tangent is 0. Well, the angle whose tangent is 0. That's the angle. So this one zeroes out, and we're left with 2 minus arctangent of 2 multiplied by the negative 2 that was on the outside of the integral. So then we just multiply it out and we get the final answer. I hope that this makes sense to you and that you're starting to see how integration by parts can be used to integrate things that up to now we have not been able to integrate. It's a beautiful method, and I hope that you've seen some of the beauty of it and just the sheer joy of it. And I hope that you'll join me in our next video, where I believe we'll be talking about trig integrals, another difficult topic, but also kind of fun.